When a substance is heated or cooled, two things can happen. Either one, the temperature can change, or there can be a phase change. In this section, we'll look at the heat associated with changes in temperature. So when heat transfers and causes a temperature change, the amount of heat transferred, Q, in joules equals mc delta T. So m is mass in kilograms. C is a constant called the specific heat, which is in joules per kilogram degree Celsius or degree Kelvin. And then the change in temperature is in degrees Celsius again, or Kelvin. So the specific heat does depend on temperature and pressure conditions, but for standard conditions, we can take that to be a constant for a specific material. It can be thought of as a thermal inertia for the substance because it gives a measure of that substance's the degree of resistance for it to experience a change in temperature. The definition is the amount of energy required to change the temperature of 1 kilogram of a substance by 1 degree Celsius. So for example, for water, the value is 4,186 joules per kilogram degree Celsius, and that's the amount of joules that would be needed to heat 1 kilogram of water by 1 degree. Example 1, how many calories of energy are required to raise the body temperature of a man of mass 80 kilograms from 37 degrees to 39 degrees as he fights off a cold? Take C equals 3,400 joules per kilogram degree Celsius. All right, this is really just a simple Q equals mc delta T question. So we'll plug into this formula here. We have 80 kilograms for the mass, 3,400 for the specific heat of the human body, joules per kilogram degree Celsius, and then times delta T, which is 2 degrees Celsius, and this gives 544,000 joules. And we can express this in calories since we're asked how many calories of energy. Calories are also used to measure heat, and this is how we measure energy in food. So 1 calorie is 4.186 joules, and this is actually the amount of energy required to increase the temperature of 1 gram of water by 1 degree Celsius. That's what 1 calorie means. So that's why these numbers look similar to the specific heat of water, which is for 1 kilogram. Usually in food, we're talking about a kilocalorie, which is 4,186 joules, or this could be called 1 calorie with a capital C, and that's what you would read on food packaging. So let's do the conversion. We'll do 1 calorie over 4,186 joules to give 130 kilocalories or 130 capital C calories. And so that could be equivalent to something like a small granola bar or a banana. 1 calorie is defined as the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. What is the specific heat value of water? Express this in joules per kilogram degree Celsius. All right, so we'll look more into what a calorie means in this section. So we're given 1 calorie, Q, which is 4.186 joules, and then this is the mass for 1 gram of water, so 1 times 10 to the negative 3 kilograms, and to raise it by 1 degree Celsius. So we have Q equals mc delta T, and then we can solve for C. We get Q over m delta T. So this is 4.186 joules over 1 times 10 to the negative 3 kilograms times 1 degree Celsius, which is 4,186 joules per kilogram degree Celsius. So we can see that the definitions of a calorie and the specific heat of water are very similar. The specific heat of water is the energy required to increase the temperature of 1 kilogram of water by 1 degree Celsius, whereas for a calorie it's 1 gram. Example 3, a small immersion heater is rated at 375 watts. Estimate how long it will take to heat a cup of soup, about 250 milliliters, from 15 degrees Celsius to 75 degrees Celsius. Treat the soup as if it were water for the purposes of calculations. Okay, so we'll need the specific heat of water, which we've seen is 4,186 joules per kilogram degree Celsius. And then eventually we want to use Q equals mc delta T. We're given delta T, this is from 15 degrees to 75 degrees, and instead of the mass we're given a volume, which is 250 milliliters of water. So we'll need to use the density of water, 1,000 kilograms per meter cubed, in order to convert that into a mass. So first let's put that in liters, that's 0.250 liters. And then we can convert using 1 liter equals 10 to the negative 3 meters cubed. So we'll have 0.250 liters times 1 liter over 10 to the negative 3 meters cubed equals 0.250 times 10 to the negative 3 meters cubed. Now with that, we can use the density in order to convert to a mass. So density equals mass over volume. So the mass of the water will be the density of the water times its volume. So that's 1,000 10 to the 3 kilograms per meter cubed times 0.250 times 10 to the negative 3 meters cubed. And this is 0.250 kilograms. And actually, because of these conversions, that 1 liter is 10 to the negative 3 meters cubed, and the density of water is 10 to the positive 3 kilograms per meter cubed, we're going to see that 1 liter of water weighs 1 kilogram. All right, so now we can plug this in. So we have Q equals mc delta T, 0.250 kilograms, times 4,186 joules per kilogram degrees Celsius, times 75 minus 15, which is 62,790 joules. And the question was, how long does it take? So we're going to use the power, which was 375 watts. And power is the work done per unit time, which in this case is the heat transfer per unit time. So we have delta T equals Q over P. So this will be 62,790 joules divided by 375 watts, which is joules per second. And this gives 167.44 seconds. When more than one substance is in contact, they will exchange energy until they all arrive at the same final temperature. This temperature is called the equilibrium temperature, and this is thermal equilibrium. So thermal equilibrium is the point where energy exchange no longer occurs because all substances are at the same temperature. And if we consider an isolated system, one that cannot exchange energy with the environment, it's thermally isolated, then we have to have overall conservation of energy applied. So in this case, if we're just talking about heat transfer, the sum of all the Q values equals 0. So we'd have Q1, oh, I'm missing a 1 there. There we go. Q1 plus Q2 plus Q3 equals 0, and so on. So 1 for each term in the system if we're just looking at temperature changes. And this means overall that at least one substance will gain energy and have Q greater than 0, and at least one will lose energy and it will have a negative Q value. And we don't have to put in the sign ourselves. This comes out naturally from the delta T in the Q equals mc delta T equation. Okay, let's look at some examples. A 750 gram aluminum pan is removed from the stove and plunged into a sink filled with 10 liters of water at 20 degrees Celsius. The water warms to 24 degrees. What was the temperature of the pan in degrees Celsius? Okay, so I think it helps sometimes to list out all our known information because there are a lot of properties here that we need for these calorimetry problems. So for aluminum, we have the specific heat, and you can look this up in a table of specific heats. So C for aluminum is 900 joules per kilogram degrees Celsius. Oh, we have the mass in kilograms. And then our unknown is the initial temperature of the aluminum pan. We know the final temperature is 24 degrees. This is because these substances, when left for a while, will come to thermal equilibrium. We know the water is at a final temperature of 24 degrees, and at thermal equilibrium, all substances will be at the same temperature, so that's the final temperature of both. Then C for water is 4,186 joules per kilogram degree Celsius. Again, I've said that one a few times, but we can look that up in a table. Delta T for water is 4 degrees, since it will also rise from, to 24 degrees, and the water starts at 20 degrees. Then instead of mass for water, which is what we need, we're given the volume, which is 10 liters. So we will need to convert that to mass. And so first let's put that into SI units. We have 1 liter is 10 to the negative 3 meters cubed. And then the density of water is 10 to the 3 or 1,000 kilograms per meter cubed. So we can plug that in here. And so we'll have the density, 10 to the 3 kilograms per meter cubed. And then I have 10 liters, which is 10 times 10 to the negative 3 meters cubed. So if you notice here, the 10 to the 3 and the 10 to the negative 3 cancel, and we're back with 10 kilograms. And so for water, you can see that we have 1 liter equals 1 kilogram. And you can remember that if you want for water. Sometimes for other substances, we'll be given the volume and we'll need the density still to convert. But okay, let's look at our calorimetry equation. So we need a Q value for each substance. We have Q for aluminum plus Q for water equals 0. So we know the aluminum will lose energy and then the water will gain energy so that this balances to 0. So M aluminum, C aluminum, delta T aluminum plus M water, C water, delta T water equals 0. I'm going to leave that together since we know it's 4 degrees, but I'll split up this one. So M aluminum, C aluminum, T final minus T initial aluminum. I usually don't put a subscript on that just because it is the same for everything. So M water, C water, delta T water equals 0. And then this Ti aluminum is the unknown. So we'll have Ti aluminum equals M water, C water, delta T water, plus M aluminum, C aluminum, T final aluminum, divided by M aluminum, C aluminum. So I've moved everything over and then divided by this term here. Okay, so now at this step, I'll move that up, sorry about that. At this step, let's plug everything in. So we have the mass of water, 10 kilograms, 4,186 joules per kilogram degree Celsius, 4 degrees plus 0.75 kilograms times 900. Are we going to have enough room? And then 24 degrees. There, just fits. All right, and divided by mass of aluminum, so 0.75 kilograms times 900. Okay, and then calculating that, we get a final temperature of 272 degrees Celsius for the pan. So it was fairly hot on the stove before it was plunged into this water. So you can see that that takes a lot of energy actually to heat water. We had 10 liters of water, which is a lot, and it still only raised its temperature by 4 degrees. An aluminum calorimeter with a mass of 100 grams contains 250 grams of water. The calorimeter and water are in thermal equilibrium at 10 degrees Celsius. 100 grams of copper pennies is cooled in the freezer to -5 degrees Celsius and are dropped in the calorimeter. What is the final temperature? Assume the water does not freeze. Okay, so again, I've listed out all the known information that we have. We need to look up each of the specific heats. We have 900 for aluminum, 4,186 for water, and 387 joules per kilogram degree Celsius for copper. And then we have each of the masses. The aluminum and the water are initially in thermal equilibrium in the calorimeter, so they have the same initial temperature. And then the pennies, this question is dated. I'll have to change that from pennies to something else, but for next time. But coming from the freezer, we have -5 degrees Celsius. So now they're all together, and our unknown is the final temperature. Okay, so one term for each when there's just a temperature change in our calorimetry equation. And then in the next line, we can plug in MC delta T. I'll split up the delta T because we don't know the temperature change this time when we want to find the final temperature. So TF minus TI aluminum plus M water, C water, TF minus TI aluminum plus M copper, C copper, TF minus TI copper equals 0. And notice I don't add any signs myself, right? The signs come out of the temperature change equation. Okay, and then we can rearrange to solve for TF. So expanding everything in a long line. So M aluminum, C aluminum. I know you know how to do this algebra. I'm just going to go through it anyway. M aluminum, C aluminum, TI aluminum plus M water, C water, TF minus M water, C water, TI aluminum plus M copper, C copper, TF minus M copper, C copper, TI copper equals 0. Okay, and at this point I want to get all of these terms by themselves. Again, my unknowns. Move the known terms to the other side and isolate TF. So I'm going to do that all in one step. So these negative terms will now become positive on the right side. M aluminum, C aluminum, TI aluminum plus M water, C water, TI, oh that one's water, TI water, TI water. And then plus M copper, C copper, TI copper. Okay, and that's all over these coefficients when we divide out to isolate TF. So M aluminum, C aluminum, where am I? Plus here, M water, C water, plus M copper, C copper. Okay. And at this point, we just need to plug in the numbers. So we have mass of aluminum, which was 0.1 kilograms, times C aluminum, 900 joules per kilogram degrees Celsius, times 10 degrees, plus the water, 0.25 kilograms, times 4,186 joules per kilogram degrees Celsius, times 10 degrees, plus one more to fit in here. Mass of copper, 0.1 kilograms. Oh, it doesn't quite fit. That's okay. 387 joules per kilogram degrees Celsius times -5 degrees is that last term. And then, so multiplying and adding all of those terms, and then we're dividing by this row right here. There we go. Okay. So that's mass of aluminum, 0.1, C aluminum, 900, plus 0.25 for water, 4,186, plus 0.1 for the copper times 387. Okay, and then a lot of space, but we can just plug that all into the calculator at this point, and it should give a final answer of 9.51 degrees Celsius. So really important to write out all of your work here, just so that you can check easily if something looks off. This makes sense because it should be between all the temperatures of what was in the mixture. So we had 10 degrees initially, and then adding -5 degrees, which lowered the temperature just a little bit to 9.51 degrees Celsius. 200 grams of an unknown metal is heated to 90 degrees Celsius, then dropped into 50 grams of water at 20 degrees Celsius in an insulated container. The water rises to 27.7 degrees Celsius, then stops. Identify the metal from its specific heat. Okay, so we have one unknown metal here. I'll call it X, and the mass of metal X is 0.2 kilograms, initial temperature of 90 degrees Celsius. Final is 27.7 degrees Celsius since everything must come to the same thermal equilibrium temperature. And we're looking for the specific heat Cx. Then we have the mass of water, its initial and final temperature, and we can add the specific heat of water. So our thermal equilibrium equation looks like this: Qx plus Q water equals 0, mxCx delta Tx plus m water C water delta T water equals 0. And then we're solving for Cx, the specific heat. So I'll have Cx equals negative m water C water delta T water divided by mx delta Tx. And then at that point we can plug in the numbers. So this is negative 0.050 kilograms times 4,186 joules per kilogram degree Celsius. And then we have 27.7 degrees minus 20 degrees. All over 0.2 kilograms times 27.7 minus 90 degrees Celsius. Okay, and then calculating that, I get 129.3 joules per kilogram degree Celsius. And if you check with the table of specific heats, you'll see that this looks like it might be lead. In the next section, we'll add in phase change terms to our calorimetry problems.